get started. The way that I will structure the course is we'll talk about theory for machine learning, and for that, I always like to motivate it by a practical problem first. We think of a problem, and then we try to model it in a theoretical way. So the way that this process works is we have an actual problem. And this problem can be, I want to classify some images, or I would like to classify my emails, or I would like to predict the next token in a sequence of tokens, or anything like that. So starting from a practical problem, we try to come up with a theoretical model. And that has many components. What is the environment? What is the goal? The goal is very important. What is the goal of my method? For that, I need to say, what is the environment? What are the mathematical objects that I'm dealing with? What am I assuming about the environment? And what am I allowed to do? Okay? So this is usually the hardest part. How do I take a problem and come up with a good mathematical model? Good means it captures the problem, the essence of the problem, and I am able to generate efficient algorithms for the problem from the theoretical model and prove that they are indeed efficient and they capture what I want. So theoretical model then gives rise to algorithms, and then I can prove guarantees for these methods, algorithms, methods. So this is the way I like to view a theoretical process for successful theoretical process for tackling a learning problem. And I'm going to start with a very basic setting today that we'll use throughout the course. So this actually is one of the most successful paradigms in machine learning. It is called prediction from expert advice. Can you see what I'm writing here? Is it fine? Is it big enough? Okay. So this is going to be a very, very, very useful paradigm in the sense that I will be able to define the environment, define what I'm allowed to do, what I'm not allowed to do, very simply, generate an algorithm, prove something about it, and this algorithm is useful. Even today's LLMs, anyone here heard of mixture of experts, for example? Right? So it's using something like what I'm going to discuss today. So very relevant. Let me define. And not only that, I'm going to do that today without any significant mathematical background, so very elementary math, okay? So let me describe the problem that I'm thinking of. Suppose that I have two choices to decide. I have a binary choice to make between two things. Should I buy a certain stock in the stock exchange or not? Should I take a certain route to work? Or whatever, binary decision, which I need to make. Now, in a single shot, and without any prior information, there is very little I can do, usually. I'm not very informed. But suppose there is additional experts that are guiding my thought process. So they are giving me advice. You should do A, you should do B. Okay? So here is the setting. I want to choose between A and B. And this can be, for example, stocks or routes in a network or experts in transformer model. Or, I don't know, any other two options that you can think of. So I'm thinking of the situation where I have, at my disposal, I have access to n experts. And each of them tells me, pick A, pick B. They tell me whatever options I want to pick. And then maybe I pick A, whatever. They all say A, I pick A. Okay, it sounds like a good idea. Turns out it was great or it was bad, and then I'm saying, okay, wait a minute, this expert over there actually was right, while all the others was wrong, and I can change my mind the next time, and so on. So clearly, in the one-shot situation, there's very little I can do, but I'm thinking of a repeated game where this choice is repeated again and again and again between the two options. So every day I drive to work, I need to decide between two separate routes and so forth. So I have to make repeated decisions. And now maybe I should say that's pretty much it. Okay, I don't want to say too much more. It's a very general situation. So first question to you is, given that I have laid down the setting, I've decided what the setting is. The setting is a repeated game. Every time I need to choose between two options. I have all these experts giving me advice. And then maybe I take the decision and see what happened. This repeated again and again and again. I'm not going to write everything I said in words down, but I think you understand the gist of it, right? So repeated game, full information. After I drive to work, I can see how much time it took me to drive to work. Oh, okay, I bought the stock. Then in the newspaper, it says how much it went up or down, and all the other stocks, how much they went up and down, and so on. What should be my goal in this setting without any further assumptions? There is no probabilistic assumptions or anything like that. So what should be my goal? That's already the first question I can ask. It's a non-trivial question. You can see. Think, maybe you cannot see. So what will be a reasonable goal in this simple setting? Yeah? Okay, you're an advanced grad student, okay? So I don't, but maybe don't answer questions in this particular lecture, okay? In the next lecture, will be fine. There are things that you don't know. But let's say you don't know about regret, and I'm not even asking about it. I didn't define regret. I didn't say what it is. What is a natural notion that you would think is a good idea to minimize in this setting? Yes, over there?
I make one decision, but I hand it off to this other thing, and I should
Yeah.
do this other thing, and now I regret that.
Okay, that is regret. I think you already, you biased the class a little bit over here. So let me tell you what I think is a reasonable goal without going into not being sorry or for something, which, by the way, is a very central notion that we're going to discuss in the course. But for now, I didn't define it. Maybe it's not a very natural thing when you're just starting out. So maybe I want to minimize number of mistakes. That's more natural than what was proposed here, no? Now, is this something feasible? Can I minimize number of mistakes? So let me, yeah, Colin? That's right. Because maybe you don't know what's going to happen. Maybe all the experts are wrong. They all gave you terrible advice. You're going to have a mistake every single time. That's not maybe a valid goal, right, as Colin was saying. So maybe everyone made a mistake, right? Or the stock market, I purchased the stock, it all went down, the whole thing crashed. The world is such that I couldn't make a good choice. But let me modify this a little bit compared to, or as little as, the best expert in hindsight. So that might be more realizable, okay? So maybe, yeah, they all made mistakes, or the stock market all went down, in which case I'm not going to be, it's not a disaster for my algorithm. It's fine, you know. I made a bad investment, but everyone made a bad investment. Okay. But if someone told me, hey, you should sell short this particular Tesla because something is going to happen, then I do want to be sorry that I didn't pick the advice of that particular expert, because there is something I could have done, right? Someone told me it. So I want to make sure that I do listen to experts who did have a good idea of what they're talking about. Maybe that's more feasible. Do you see the difference between that and what I said before? Yeah? Okay. So this might be a realizable goal. Now, that completes the first part of setting up the problem and theoretical model. So problem, I think it's clear that this is a useful fundamental problem, right? I don't need to justify it too much. It's a very clean setting. I didn't really, you can see that you can apply it in very, very general situations. Theoretical model also, I almost didn't make any assumptions here. Such a basic, clean thing to say. Let me get to the algorithm method. So can someone please propose to me an algorithm that will be able to compete with a good expert, assuming that there is one? Or well, you don't even need to assume one. The best expert. I have a bunch of experts. I have a set of them. And every iteration, I choose the advice of one of them, and I make a decision, and so on, A and B, and then I see it's wrong or right, and so on. And I want an algorithm. You see it's an algorithmic problem, right? Here is an algorithm, silly algorithm. Pick one at random. Not going to do well at all, okay? But it's some algorithm. I pick the advice of one expert at random. Obviously, it's not going to make as little mistake as the best expert in hindsight, because maybe there is an expert that got it all right, but I'm always picking one at random. It's not going to do well, okay? Now my question to you is, give me an algorithm that is better than this silly random algorithm. Yeah, over there. Okay, wonderful. Good suggestion. Thank you. Your name? And you're undergrad or grad? Okay. So David suggests the following. How about I have these experts, expert 1, expert 2, expert N. And then I keep track. Maybe this one made 5 mistakes, this might make 3 mistakes, and so on. That's my mistake. And then I pick the best expert in terms of how many mistakes it made in hindsight. Question over there? Okay, so then no whispering, because it kind of is in my ear, I cannot concentrate. Okay, so pick best expert in hindsight. That's algorithm 1. Seems like a good idea. Well, does this algorithm have a guarantee that is comparable to the best expert in hindsight? That's a theoretical question. I can now have I have a valid theoretical question, right? Maybe yes, in which case I need to prove to you that yes. Maybe no, then I need to prove to you that no. So let me prove to you that this expert actually does not compete with the best decision in hindsight. So let's see that. For that, I need to show you a construction. I need to show you an example, a setting, where this thing doesn't satisfy what I wanted. Okay? So let's say I have 2 experts, and then this one always say A. So he always says A, pick A. This expert always says pick B. Now the truth, or the correct decision turns out to be something like A, B, alternating. Okay? Everyone understands the setting I'm describing? Now, in iteration 1, these experts are the same. Which one do I choose? Well, you didn't specify, David, but I can decide, arbitrarily, right? So maybe I choose B. Then I say, oh, wait a minute, A was the correct answer. So next iteration, I'm going to pick A. Then B got it right. And then I'm going to pick B next time, and A is going to be right, and so on. Okay? So I will always pick, you see, the wrong decision. So this particular situation, I just showed you a setting where a number of mistakes is T in T iterations. Okay? But the best expert in hindsight has how many mistakes? Half, right? Half T over 2. Okay. I could have, by the way, made it worse. I mean, I could have created N experts here, and then the best in hindsight will be T over N, and I always make T mistakes. I could have done it too by some round robin kind of thing. So, but this was a good suggestion, by the way. We'll return to this suggestion because there are some modifications of it that make it work but just the vanilla one is no good. By the way, you can already see here, those of you who have some experience in probabilistic algorithms and have background in probability and statistics, you can see that this behaves very, very differently from statistical theory. In statistical theory, if you have a process, law of large numbers says that you will approach the mean of whatever process it is you're looking at in the limit, right? So if you pick the best in hindsight, it is going to approach whatever is the best, it's going to do best in the limit. But you can see this behaves very, very differently. This was an advanced remark for those of you who understand what I said. Okay, so this doesn't work. Let's try something else. Any other suggestion? Uh-huh. Okay. Okay, so you're saying let's still keep some kind of metric of performance that is related to how well the experts did, but maybe don't be so harsh, because this is kind of a brittle thing. When did I hit the expert with the wrong decision? Exactly when they were all even. So let's kind of make it a bit softer and keep track of how well each expert did, and then maybe assign weights according to that, right? Okay, that's a good suggestion. Your name? Okay, thank you. So here is some kind of formal way of making your suggestion into an algorithm. It is called weighted majority. Weighted majority. This is an algorithm due to Littlestone and Varmuth. In '89. And it's a very nice algorithm. And Manfred Varmuth is a pioneer in theoretical machine learning that we'll talk a lot about his contributions in this course. So here is the algorithm. So we keep a weight for expert. So let WTI is the weight. And then initially, W1I is going to be 1 for all I in N. So initially, the experts are all going to have weight of 1. Because I don't know which one is better. And then, for t equals 1, 2, and so on, every iteration I have to pick an expert first, right? So I pick an expert. So let WA of t is going to be the sum over all experts that say I says A, WTI, and similarly WB of t. I also going to sum up all the experts that say B. And then if WA is bigger than WB, then I say A, and otherwise B. So I pick according to the majority. And if there is a tie, then I break it up, arbitrarily here. I said bigger than. So if there is equality, I pick B. Then I see the answer. I see the truth. And then I update. So if I made an error, then the weight at time t plus 1 of the ith expert is going to be the weight at time t times 1 minus epsilon. So I reduce the weight a little bit. But if this expert was right, then I don't reduce the weight. And notice that I don't need to normalize to 1 or anything like that, because anyways, I only look at the relative between the two things. If you want, you can normalize it to avoid numerical stability issues, but you don't have to. Okay, questions about the method? Until what time do I have here? 2:40? Okay, very good. Any questions? Make sense? Yeah. Okay, so here is our first theorem for the class. So let me denote by MT number of mistakes that the algorithm makes. Time t, up to t. So little t I usually denote time, and time goes usually from 1, 2, 3 up to big T. That's kind of the notation I like to use. Then this MT is less than 2 times 1 plus epsilon times MTI star plus 2 log n over epsilon, where MTI star is number of mistakes of I star. I star, this is true for any I star. So for any I star, which is an index from 1 to n, and in particular for the best expert, the algorithm guarantees that it will make at most roughly up to factor 2 mistakes of the best one, plus something that behaves logarithmically in the number of experts. Any questions about the theorem? I was just reminded of, yeah?
What's that line
Next to this, this log, natural logarithm, yeah. Is it clear what the theorem is saying? I mean, maybe you don't understand why it's true, but at least you should understand what it's saying. It's saying that this algorithm is a good algorithm, right? It makes at most double mistakes in the best expert. So let's say the best expert made 0 mistakes. Then it's going to make like logarithmically many mistakes, which is very little, right? Compared to, doesn't grow to infinity with time. And look what a natural and simple thing method I'm giving you. Clearly, it's very efficient. You don't need to keep too many variables. You don't need to do anything drastic here. Ella, what's the question? You can ask me. Yeah, this is true for any expert, in particular for the best expert. So I could have written here min over I, but it's just true for any I star. I just remembered something I should have said. If anyone here needs special accommodation in terms of the microphone or something like that, please come to me at the end of the class and let me know, okay? Sorry, I forgot to say that in the beginning, but if there is anything special accommodation that we can provide, then let me know. I'll be happy to assist with it. Any other questions? Yes?
What about doing the inverse? Like one expert
Yeah.
body choice also reduce the inverse.
Oh, that's a very good point. You're saying, what if someone gets it all wrong?
Yeah.
I should always do the opposite of that person, right?
Yeah.
Okay, I like that point. How would you, question to you guys, to all of you, how would you incorporate that? I claim that this algorithm can handle this situation. How would you incorporate it? Yes, over here? Uh-huh. Very good. Your name? Kara? Very good. Kara's suggestion is the following. See, sometimes you do need to think a little bit outside of the math and just think, what's happening here? What's happening here? And the thing is, you could have created, I have n experts, let's create 2n. Who cares? Anyways, it comes into the logarithm. Log n, log 2n, it's another difference of 1, right? It's really not a big deal. So let's create 2n experts. For every original expert, I have himself, and then I have another one that says the exact opposite of what he said or she said, okay? So when you do that, automatically you compete with the best expert and the best negation of the best expert, Okay, whoever asked me, I didn't see. But yeah, makes sense? Oh. Very good question and very good answer. More questions? Yes?
Just clarification. MTI star is the number of mistakes made by the mass of I into the absolute, or is it the number of mistakes?
Okay, let me define it more. I kind of use the notation which you're right to ask me about, but kind of it all makes sense. I mean, so I defined MT to be the number of mistakes up to time t of the algorithm. Then I will define MTI is number of mistakes of ith expert up to t. So up to, including. Okay, so 1, 2, 3. How many? Sum up all the mistakes he made up to time t. That's what MTI describes. Okay. And I also add here W. This I already defined. WTI, that's the weight of the ith expert up to time t. And WA, WB, that I defined too. Yeah? Oh, this is true for any epsilon between 0 and, let's say, half. So I can pick an epsilon I want. Yeah, some parameter of the algorithm. And the choice of the optimal parameter is what? You can solve some quadratic equation here and figure it out, right? It depends on how many mistakes the best expert did. But I can maybe tune it. So that's why on purpose I didn't tune it. I left it out as a parameter. Any more questions, or should I go to the proof? Let's do the proof. But mathematically, you're all fine. With the notation I gave here, no more questions. Yeah, everything is good. Okay. By the way, this is written in detail in the textbook, the first textbook for the course, chapter 1, very precise over there. You can go over it at home. So let's prove. So for the proof, I'm going to use a potential function. So I'm going to define phi of t is going to be the sum of all weights of all experts up to time t. And then phi of 1 is equal to what? N, correct, because they're all 1 in the beginning. Okay, the proof is extremely simple, which is why I chose it for the first lecture. And it goes by 2 observations. The first one of them is very easy. So let's look at phi at big T. Big T, again, is the last time iteration. Little t goes from 1, 2, 3 up to big T. That thing, that's equal to the sum of all the weights. And the weights, they started 1. They keep on being multiplied by 1 minus epsilon. They cannot be negative. They're all non-negative, right? Non-negative numbers. So, of course, this is bigger than WT I star for any I star. And that is equal to 1 minus epsilon to the power of MT I star. Everyone agrees? Okay. Number 2, let's look at phi t, t plus 1, little t plus 1. And I want to see how it changes between the two, between iterations. Okay. So, question over there? I star is the best expert in hindsight. It can be any expert at all. I sum up n numbers, and they're bigger. They're all non-negative. Then they're bigger than any one in particular. right? Okay. So what is phi t plus 1? So I have here, this is the sum of all the weights of all experts that said A, or let me say, all I that were wrong, and they got multiplied by 1 minus epsilon, plus the sum of all the experts that were correct, and they got multiplied by 1. Nothing happened to them, right? So this is equal to the sum of all weights, which is phi t, minus epsilon, sum of all weights that were wrong. And I claim that is at most phi t times 1 minus epsilon over 2. So why is that? That's kind of the only non-trivial step in the proof. So I claim this is at most half of the weight. At least, sorry, this is at least half of the weight is on those that were wrong. So, okay, let's do the following. So this is if I made a mistake, I should say. If algorithm made mistake, right? Then I claim this happens. So why is it true? Yeah.
It's exactly what you just clarified, which is that if the
Yeah.
algorithm made the mistake, then the weight of the side that gave you the wrong answer.
Right.
The side that gave you the
Right, right. Because that's how I define the algorithm, right? So if I didn't make a mistake, okay, God knows. I mean, well, if I didn't make a mistake, then phi of t plus 1, it didn't grow. This is always true. It can never grow. I only multiply weights by 1 minus epsilon, can never grow. I never increase the weights, I only decrease them. But if I made a mistake, then I claim that I lost some weight, you know, and how much weight did I lose? Well, I sum up all the weights that were wrong, and that's at least half of the weight, because that's how I make a mistake. If I see if it's bigger than those who were right or not. If I didn't make a mistake, then I cannot say that. But if I did make a mistake, half of the weight was wrong. Okay, so I have two observations here. Let me recap. This sum of weights is bigger than that of the best expert because they're all non-negative weights. Then the sum of the weights, it never increases. Doesn't matter if I was right, the algorithm was right or wrong. And if it was wrong, then it decreases by at least some substantial amount, which is a multiplicative factor of 1 minus epsilon over 2. So let's add these two things together, okay? So then I have phi at time t. This is bigger than w 1 minus epsilon to the power mt of I star for any I star. And on the other hand, it's less than phi t minus 1 and phi t minus 2 and phi t minus 3, but multiplied by 1 minus epsilon over 2 to the power of mistakes that the algorithm made. Okay? Any questions? So let me take the logarithm. So what I have here is mt of I star, logarithm of 1 minus epsilon. Okay, this is equal to n 1 minus epsilon over 2 mt. And here I have log n. plus mt log of 1 minus epsilon over 2. So I'm going to use the identity that log of 1 minus x is less than minus x, but bigger than minus x squared for x in 0, 1/2, which you can verify. And therefore, what I have here is empty I star times negative epsilon squared less than log n plus or minus mt times epsilon over 2. And if I shift side and rearrange, I get exactly that mt is less than, so I have here 2 log n over epsilon plus 2, 1 plus epsilon mt of I star, which is what I claimed. Any questions? Yes. Can you tell me, ask again, please? Ask again, please, I didn't hear. Over here, you're asking?
Yeah, I understand it.
Yeah. Okay, let's look back. This is kind of the key point, okay? Look at the algorithm definition that I wrote there. If WA bigger than WB, then I say A, otherwise I say B. So it's a sum of weights, right? I look at the sum of weights, not how many experts, sum of weights. Sum of weights is exactly phi t, right? At least half of the phi t said the wrong decision if I made a mistake, by definition of the algorithm. Okay? Everyone sees that? That's the most important point, actually. You're welcome. Yeah, everyone okay with that? Questions? Okay. So this is a nice, very clean, very easy theorem and proof and algorithm. Everything here is very clean, very elegant. It's deterministic. It holds always. It doesn't matter if what the experts are predicting. Is it Stokes? Is it routes? It doesn't matter. It doesn't matter if the environment is adversarial or not, or what the actual results are. It's a very powerful statement because I made so few assumptions. So that is something I want you to remember, okay? It's a very key thing in theory. The less assumptions, the more general setting that you think of, the more powerful the result is going to be. There is something here. By the way, this is also a deterministic result. So the theorem I stated here, over there, is true always. There is no conditions. Always, always true. There is something a bit maybe dissatisfying, which I think you asked me over here, which is the half, the factor 2 here, that maybe I lose. Because it's true, I compete with the best expert, and if the best expert was phenomenal, it had very little mistakes, okay, factor 2, not a big deal. But it could be the case that he or she makes a lot of mistakes, right? In which case, factor 2 could be a lot, right? So, 2 questions for you. Let me start with the simpler one. So here's how I really want you to pay attention now to what I'm saying, because this is how I think of as a theorist. Is this factor 2 really there? Can we improve it, or is it important? Is it somehow inevitable that I have to sometimes do twice worse than the best expert? And let me restrict 1 minute for deterministic algorithms, which means no probability, no randomness, no nothing. I make a decision. A, and then B, and then whatever, according to the experts. Is it really the case that I have to pay 2? If you get it right, I'll give you a bonus. I'll remember you favorably if you answer this correctly. Yes.
We change the algorithm, like how we decide which one to take. Like say like 2/3 of majority.
Yeah. You're asking what will happen?
Or I mean,
It's a question, or you're answering my question, or you're giving me a new one. That's a good trick. I'm asking a question, ask me another one. Okay, so you're asking me a question. You're asking if you change the probability, the kind of the threshold of between half to 2/3.
but then sometimes it will not.
Um,
If it's really close.
well, it's not well defined. In a sense, I mean, you're saying if someone has 2/3 of the votes, then choose what they're saying. But what if no one has 2/3, right? Then you're kind of in trouble. So it's not a well-defined algorithm. You need to give me a well-defined choice. Yeah, okay. One expert, what can I, of course I compete with the best expert. Okay, this is a good point. So I want to, look, I defined a framework here, and the framework, the generality of it comes from the fact that it allows any kind of arbitrary experts and arbitrary solutions, arbitrary results. So when I ask, is it true that in general you need a factor 2? What I mean is over all possible instantiations of this situation, do you need a factor 2? Yeah?
Because you need to like deterministically break ties with two options.
Yeah.
You need to have factor 50%.
That's your intuition. Your intuition is correct, but I want a proof. Otherwise, no bonus for you. Can you prove it?
Like at worst, you're going to have 50% or 51% of the experts doing, like you're going to have like a split between the two sets of experts giving like the correct option. And that's worst case.
No, look, your intuition is correct, but this is a mathematical course, okay? So I want a proof. Prove to me that you need to pay factor 2. You have aha, very good. What's your name? Michael. Grad or undergrad? Grad. Okay. I really hope the undergrads will be more involved here, but good, I'm happy with you too. So that is correct what you said. Michael said the correct thing. So remember the last example I had when we have A and B, and then one expert said always A, then the other expert says always B. Now what can happen? They don't have to be like that, but here is the crux of it is the following. In a deterministic situation, I have to make a decision. Me, I mean the algorithm. Now, here is a setting. I'm going to be a bit more formal. You kind of got the gist of it, but if I want to make it formal, please listen to me very carefully. This is a good homework. Do I have it in the book? Can you check? If I don't have it, I want to add it. This is a really good exercise. No. Just the following kind of theorem, which I'm saying. For any deterministic algorithm, has to make at least twice mistakes. It's not. Look, it's easier than that. So here is the reason. I have to make a decision, and I can have the environment. I didn't restrict the environment. The truth can always be opposite of what I said, always. Okay. So I'm saying A. No, the truth is going to be B. I'm saying B. Truth is going to be A. Okay. So think of this situation. How many mistakes am I going to make? Always mistakes. So T. This is inevitable in this situation. But I could have two experts. One of them says always A. The other one says always B. And one of them is going to be correct half the time, right? Just by the way I defined it. So one of them is going to make less than half mistakes than I did. Is what I said clear? Now, if you're not sure if this is kind of a good course for you, what I said now should be, you should be able to make it into a proof, okay? Into correct, precise proof. And generally, everything I'm saying, this is an easy class today. Everything should be, I hope, crystal clear to you. So, what I said now can be made into a formal proof that factor 2 is inevitable. This less than equal to is tight. But then you can ask yourself, wait a minute, then should I give up? I mean, can I never ever do anything better? And I kind of hinted at I think you had the right intuition over there. So I am committing to something. I'm committing. The reason I'm able to give you a lower bound is because I'm committing to an A or an B. But I have randomness in this world, and I can choose I can have a randomized algorithm, and the randomized algorithm can say I pick A and B with probability half. Okay? In which case, that will break my lower bound. It will break because in this exact situation that I said, I predict half-half. What is the nature going to do? The environment doesn't have something that will make me mistake for sure. It can cause me to make a mistake on expectation on half. I think you're talking about the root T. That's what you're saying, the Bernoulli. Oh, okay, but that's a harder exercise. What I'm saying now is an easier exercise, the half. Okay, good. So then theorem, small theorem, factor 2 is tight for any deterministic algorithm. Now let's continue. Can someone give me a randomized algorithm that does better than weighted majority? Yes, Colin. You were going to too complicated of a situation. Yeah, Bavi? Ah, okay, very good. So how about let's change the algorithm a little bit. And as some of you said, many of you said, this commitment thing is what made us fail. It's inevitable, but this kind of hard decision here is problematic. Okay? So let me change the algorithm. And the new algorithm is going to be called randomized. Randomized weighted majority. It's also due to Littlestone and Varmus in the same paper. So I don't need to change a lot of the words here. And then the change is very, very simple. I initialize weights. Weights are going to be the same. I update them the same. But my decision is going to be different. My decision is going to be randomized. And it's going to be randomized according to the weights. So instead of summing up A and B, I'm going to create a distribution, PTI. The probability of picking expert I at time t is going to be her weight at time t divided by the sum of all experts' weights at time t. And then pick I according to this probability PT. So instead of, and update the same, exactly the same. Then I see the truth, then I update. If they made a mistake, they didn't make, I chop down their weights, and otherwise I don't. And everything is the same. Rules of the game are the same setting. The only thing that changes is my commitment to the decision. It's not going to be a hard commitment, but it's going to be a soft kind of commitment. I'm going to make a distribution. Yeah? Question about the algorithm? Yes? I don't completely hear you well, and also, can you please repeat it, but just a bit louder?
Yeah, sorry. I guess what I was asking is, so like, this turns into like basically it knows the algorithm is
Yeah.
randomized.
Oh, okay. You're asking, I think the question is here about the environment. So is the environment allowed to know the algorithm that I'm picking, and can it adversarially pick the results according to my algorithm? And the answer is yes. This is a very general setting. The environment can do whatever it wants. It can see what my algorithm is doing. For a deterministic algorithm, it's clear what the min-max is and so on. This is a notion from game theory, which we're going to discuss later on in the course, min-max. If you don't know what I'm saying now, it doesn't matter. But The way randomized algorithm, this is something all of you have the prerequisites, you know probability and you know algorithms, randomized algorithms. The way randomized algorithms work is the following. You pick a decision, so the environment is allowed, or the adversary knows your algorithm, that's fine. They know what you're gonna do in terms of distribution. They know you're gonna play according to distribution, but they cannot see the coin flips of the actual distribution. So that is hidden from so the way the protocol is, I pick a distribution, or the distribution, so then the environment can pick whatever result it wants adversarially, and then I draw from the distribution. So it cannot see what you draw and then pick the result, because that would be deterministic, the same kind of thing as deterministic. If it can see, oh, I choose A, it's gonna give me a B. The same counter example I gave before would work, okay? So this is standard in randomized algorithms. The environment is allowed to see your distribution, but not the coin flips of the outcome. Yeah, makes sense? Okay, yes. Well, the setting is like this. For any sequence of A and B, and the sequence of A and B can be determined online with seeing the P's, and then pick the A and the B, that's fine, but cannot see the outcome of the P, okay? Now let me tell you what improves for this algorithm. So the theorem is let MT be the mistakes the algorithm makes up to time T, same as before, epsilon is the same. Then, but now this is randomized weighted majority, not weighted majority. So what I can say now is for every I star, something happens. Now what happens? I have now, the number of mistakes I made is not a deterministic quantity, it's a random variable. So this is a random variable. MT is a random variable. Cannot talk about it deterministically. So I need to say something about the expectation of this random variable. And the expectation of how many mistakes the algorithm makes is at most what I had before, but no 2. No 2 here and no 2 here. So I got rid of the factor 2 because I didn't commit to a particular decision at iteration T. The price I pay is that I'm talking about the expectation. It's no longer a deterministic algorithm. It's a randomized algorithm. Nevertheless, I can make statements about this happens with very high probability and so on, which I'm not going to do in this class. Yes? Yeah, that's a good point. I could have done it over the action space. It's possible to do it. And I could have analyzed in a similar way. But over the experts is more general because it might be the case, as we will see later on, that the experts don't commit themselves to only 2 things, A and B. Maybe they have complicated things they're saying. And then I don't really want to go to the solution space. It's going to be a very verbose and very inefficient way to represent what will happen. Okay? So this is more general and also cleaner for the proof. Any other question? Okay. So proof is clear. Not proof, sorry. Theorem is clear, what I'm saying about the theorem. So I now claim something about the expected number of mistakes I'm making. And this expectation can be converted to a sequence of conditional expectations. Given everything so far, the next random mistake is going to happen with probability and so on. I'm not going to do that either here. So it can be a martingale. If you heard that before in probability analysis, I can convert it to a martingale. Good. So the proof is surprisingly similar to the proof I already have. So let phi t be the same sum of weights as I had before. The weights, again, are updated according to the law that I had here. These weights are deterministic. They are not randomized, right? So the experts make all these predictions, and I update them. They're not random variables. Phi 1 is n, just like I had before. Okay. I guess I do want to define one more quantity, which I will do it here. So let MTI is going to be random variable of, sorry, MT. It's a random variable of whether the algorithm errors in time t. So big M is everything up to time t, and little m is just over that particular time step, little t. So this is a random variable. Now, let me do the similar analysis to what I had before, but this time I have to keep track of the fact that it's a random variable I'm analyzing, and it's different than the kind of hard binary decision I had before. Let's look at the sum of weights. In the end, bigger than any weight in particular, and that's also bigger than 1 minus epsilon by definition, time number of mistakes the ith expert make. This observation, same as before, true. I'm now not going to partition my analysis into two situations of what happens to the potential before whether I make a mistake or not. I'm not going to do that. So I'll do something different. Let's look at phi time t plus 1. This is equal to the sum of the weights of the expert, ith expert, 1 minus epsilon times whether it made a mistake or not. So now, so this is whether the ith expert made a mistake at time t or not. This is equal to, by my definition of probability, so what's the sum of weights? That's phi t. And what I have here is 1 minus epsilon summation over I, pt of I, mt of I, by the way that I defined pt of I. So pt of I is the weight of the ith expert at time t divided by the phi, divided by the sum of weights. This is algebraic equality. Now this summation of probability times whether the ith expert made a mistake is what? That's kind of the key quantity. Good. Expectation. Exactly right. So this is equal to phi t, 1 minus epsilon, and here I have the expectation of whether my algorithm made a mistake at time little t or not. Okay? That's the key kind of step. And this is less than or equal to phi t e to the minus epsilon expectation little m of t. Because 1 minus x is less than e to the minus x. This is always true. So let me see what the two inequalities give me. The sum of weights at the end is bigger than 1 minus epsilon to the sum of mistakes the I star expert did, just as before, because every time he made a mistake, I multiplied him by 1 minus epsilon. This is less than phi 1, and then recursively I have here e to the minus epsilon, the sum over t expectation mt, which is equal to n e to the minus epsilon e of big MT. Right? So the sum of expectations of the individual error is the expectation of the overall random variable, the narrative of expectation of how many mistakes the algorithm made. I can take the logarithm, and what I have here, this is the same log n, and here I just have minus epsilon, so it's even a simpler expression, minus epsilon expectation mt. So using this inequality again, only one part of it I have that this inequality here. So mt of I star times minus epsilon squared less than log n minus epsilon the expectation of the mistakes. And shifting sides and divided by epsilon now, there is no 2 epsilon. I get the theorem statement, again on the expectation with an expectation on the number of mistakes. So yeah, that proves my claim. Any questions about the algorithm or the theorem or the proof? Or why it's interesting or why it's important? I hope it's clear. This is a very elegant theorem, very general, and very clean statement and very clean proof too. It's a very simple proof. Now I can ask a similar question to before. Is it the case that I can never, ever, ever make less mistakes than what's written there? So 1 plus epsilon times the, so I remove the factor 2, fine. I know that factor 2 is necessary for deterministic algorithms, but what about, well, epsilons can be very small, that's fine, but is the log n there necessary, and the trade-off between 1 plus epsilon and 1 over epsilon, is this a necessary trade-off, or can I do something better? Even with the power of randomness, okay? And what do you think the answer is? So I do want to give you a taste in this course of how I would think as a theorist. Okay, so I analyzed the deterministic case, I got a tight algorithm, I saw it's inevitable. We did a randomized algorithm, we proved something for that, much better, wonderful. Can this be improved? Yeah? Okay. What was your guess? Okay, that's a good point. Anyone else? But you see, I'm not done. I mean, I could still ask, is this tight? So this is what Rahit was saying before. We will see later in the course that actually, in full generality, in some sense, it is tight. And the way I would see it, you can ask, what's the best epsilon? How do I know what the epsilon is? You guys asked this a little bit. What is epsilon? Some number. Okay, now I want to run my algorithm. What should I put it in? So what's the best epsilon you can pick? Let's do a small calculation. I'm going to write on this clean thing now because we are near the end of the time. I hope that's fine with everyone. Okay. So what's the best epsilon? We have something like 1 plus epsilon times mt star or mti star plus log n over epsilon. I'm on purpose not putting the expectation here and all of that, just kind of to keep the notation clean. So you can see that the best epsilon is something like square root of mti star log n. And then this will be something like mti star plus square root mti star log n. This looks pretty good. So this Clearly, it's inevitable. You cannot do better than the best expert, and that is the homework. I hope this is clear, and you cannot really hope to do better in a situation that you make decisions and you don't know anything beyond the information that's given to you. So all the information given to you is the experts. Best you.
MTI starts with a negative.
Correct. Yeah. So.
That is correct.
Yeah. Divided by, right? So like this. Yeah. Thanks, Rohit. Yeah. So, but that will give me, this is correct. So that's the bound that I will get. And now the question is, can I improve upon that? It turns out, in general, you can't. So there are situations where this behaves like number of iterations, and then the square root t and even the log n are going to be tight, up to a factor which is very close to 1. It's actually a factor 2 what I get here, I believe. Right? You'll get root 2. So the root outside or inside, maybe outside. But even that, they can be improved, and you can do all sorts of nitty-gritty modifications. But then you can ask, as a theoretician, is my job done? And in some general, if you're in some sense, yes. This is already a very clean theorem. It's very applicable. It's applied, as I said, in many, many different situations. We'll see many of them in the course. But you could take this further. What if I look at more refined quantities than actually MTI? And someone was saying that, I believe, before. What if one expert does all the same, or they have very little variation between them? So you can, for example, define variation. Variation will be something like summation over t, mt of I, minus mu t squared, where mu t is the average decision in some sense. And then you can look at that and see, maybe I can bound my regret into this kind of loss in terms of something which is a bit smaller. And you can even do more refined things. So maybe summation mt of I minus mt minus 1 of I. And then you can ask, is this tight? Is this tight? And if not, can I do something tighter? And so on. And there is a long line of research that has indeed investigated these quantities and come up with better and better bounds and more sophisticated algorithms. So that's kind of the way the theory process will work. So you're always trying to attack it from both sides. Jerry, 1 second. So you're always trying to think, am I tight? If not, what am I missing here? What's the situation that I would like to capture? I like to motivate it. I wouldn't go there if there was no good reason. But in situations, there are many times good reasons. There could be situations where the variance of experts are huge. And some experts have very little variance. Then it's a very natural question. I have one algorithm that's, the experts are algorithms. One of them is very stable. The other is very noisy. Can I take advantage of that? And in many practical situations and optimizations, there are. And then there is a reason to dive into and make a stronger algorithm, make a stronger claim. But I always like to, again, going back to the beginning of class, I like to go to the motivation. Motivate the problem. Otherwise, what's the point of doing all the math if you don't have a really interesting, clean problem? At that point, you can try to think of a framework, analysis, theorem, so on. Yeah, Jerry? Okay, so the reason what I said here, I've been a part of this research, but it's not like, this is a real line of investigation. It's not something that was made up for no good reason. So there are situations, even though this looks like a lower order term, and it is a lower order term, many times, especially if you get to performance environments. In today's LLM world, you're trying to minimize perplexity. 0.01 perplexity is huge, as you know, right? So you really want to make sure that if there is whatever tiny little advantage you can get hold of, you exploit. So removing the variance, for example, is very well motivated. So the answer is yes, but we might get there later in the course. There is reason to look into final grained bounds, and I will give them. Okay, we're done for today. See you all Thursday. Yeah, let's publish it, and the exercise too.